Let's talk about fluids, and that is basically inclusive of gases and liquids. Fluids could be stationary, then we talk about fluid statics, or they could be flowing, and then we talk about fluid dynamics. We recall the defining equation for density as the mass divided by volume, and the defining equation for pressure as the force over the area. Now, any of these, you know that there are multiple units that you can use. For example, for pressure, you get all those, but the SI unit will then be the Pascal. Now, the pressure on a static fluid is normally referred to as hydrostatic pressure and is given by this equation where P0 is the atmospheric pressure, ρ is the density of that fluid, g is the gravitational acceleration, and h is the depth at which you are measuring that pressure. And that pressure will be referred to as the absolute pressure. Now, when you take the absolute pressure and you subtract the atmospheric pressure, you get what is referred to as the gauge pressure. And this is because fluid pressure gauges are set to read 0 at atmospheric pressure. So it's more like they are neglecting atmospheric pressure. Now let's look at Pascal's principle, which basically explains the transmission of pressure inside an incompressible liquid. Now if you consider a container with a liquid as shown, and you exert an external pressure using a piston, pressing it down, the external pressure will change, and so will the internal pressure inside the liquid. And what Pascal suggests is that the change in internal pressure will be equal to the change in external pressure. Now, if you take a system like this, which has two volumes connected to each other, the change in pressure on one side will cause a change in pressure on the other side. You can also note that the volume change will be the same. You can write the volume change as the product of the area and the stroke length, and we can also note that the work done on one side will be the same as the work done on the other side. The other principle that I want us to look at is the Archimedes principle, which simply explains how or why things float in fluids. And it does this by acknowledging the fact that when you place an object on a fluid, there will be a force that's pushing it upwards. And the object could be floating completely, partly submerged, or fully submerged. The weight of the displaced fluid will be equal to the buoyancy force, which is the force that the fluid is pushing upwards on an object with. And this is why objects feel lighter when placed in water, because the apparent weight is equal to the actual weight of that object minus the buoyancy force. Now let's talk about fluids in motion and differentiate ideal fluids from non-ideal fluids. Ideal fluids are always flowing steadily, or in what we refer to as laminar flow. And the non-ideal fluids could have turbulence. The steady flow simply means the molecules are moving in a straight line, whereas in the turbulent flow, there's some kind of destructive behavior. Secondly, ideal fluids always have constant density throughout, whereas non-ideal fluid could have some parts of it being more denser than others. Ideal fluids have what we refer to as non-resistive flow or non-viscous flow, meaning there's no viscosity in those fluids, whereas in real fluids, we have viscosity. And this is why it is difficult to pour honey out of a jar compared to ordinary water. Ideal fluids also have what we refer to as irrotational flow, meaning there's no rotation about the center of mass of the fluid, whereas the real fluids or non-ideal fluids could have that rotation. All right, now we can combine the static pressure with dynamic pressure through what we call the equation of continuity, the static pressure is given by that equation, whereas the dynamic pressure is just the kinetic energy of the fluid, where P0 is the atmospheric pressure, rho is the density of the fluid, g is the gravitational acceleration, h is the depth where you are measuring the pressure in that fluid, and v is the speed of the fluid. Now, combining these two equations, we get the total pressure as the static pressure plus the dynamic pressure, and that gives us what we refer to as the Bernoulli's equation. There are loads of explanations and examples of Bernoulli's equation, and we'll look at various examples during the tutorial. To illustrate Bernoulli's equation, we can also use the venturimeter, which measures the flow rate at different points with different flow areas. And what we realize there is that the flow rate at both points should be the same at point 1 and 2, Q, which should be the same. And we can then literally be able to find the change in pressure at the both points using that equation, including finding the velocities at either of those points. Now, to summarize what we've spoken about so far, we talked about gauge pressure, which is given by that equation over there in static fluids. We also spoke about the absolute pressure, which is also represented there. And we also spoke about the dynamic pressure when fluid starts to flow, and that's given by that equation. We said we can combine the two into an equation of continuity, or P total, that's made up by the sum of those two. And the equation is called the Bernoulli's equation. We also looked at two principles so far, one of them being the Pascal's principle. And the Pascal's principle was basically saying the change in pressure externally on a system should be equal to the change in pressure internally. That's for obviously a closed system. And we looked at Archimedes' principle that explains why things float in fluids. And we said that the buoyancy force is equal to the weight of the displaced fluid. We then said that when objects are placed in fluids, they'll have an apparent weight that's given by that equation. Let's meet again during tutorials where we will be looking at examples of each of those principles as described. Thank you.